Starting with the numericals of exercise C of current electricity. Over here, the first concept that you have studied in standard 9, that if you want to take a charge from one point to other point, then the potential difference between the 2 points was work done to take a unit charge. So basically, the formula that we studied was potential difference was work upon charge. So therefore, I'm going to write work done is potential times the charge. So remember, W is the work done, which is energy, okay, which is potential times the charge. So this is a formula number one. Now we know that electricity is defined as rate of flow of charge. So that is the reason why we have charge is equal to current times time. So I'm going to write over here V, and in place of Q, I'm going to write IT. So this is my number two formula. Again, I have Ohm's law, that is V is equal to IR. So on substituting in place of V, IR, okay, I get a formula which is equal to I square RT. Now, this is a formula that is used to calculate the heat energy when the current is flowing for a certain amount of time, and the resistance is also given. This is also called as the Joule heating effect. Okay, so if you allow the current to flow for a longer time, more heat will be produced. If you double the current, then you have heat produced will increase 4 times. So all that is there. Now, Ohm's law can also be written as I equal to V upon R. So in place of I can substitute it as V upon R. So W is equal to V upon R into T. So W is equal to V square upon RT. That's formula number 4. So these are the 4 formulas that I have for energy or work done. And now I'm going to write it for power. So power, we know it is work over time. So therefore, in all these formulas, if you divide by T, so I'm going to get power. Power is W over T. So you can see that everywhere you have a T, that T is going to go away because you are dividing by T. So I'm going to get power is V into I. I'm going to get power as I squared R, and I'm going to get power as V squared upon R. So these are the formulas, okay, to calculate electric power. Fine. Another point that you need to keep in mind is when you talk about energy, energy is equal to power into time. So when you express power in kilowatt and when you express time in hours, the electrical energy that you get, okay, is kilowatt hour. So the electrical energy is kWh. So when you're expressing power in kilowatt and you're expressing time in hours, so that is important for you to remember. Okay, right. So this is a very straightforward question that is expected to be asked in an exam. So a heater is rated 1200 watt, 220 volt, and it is used for 2 hours per day. Calculate the energy consumed in a week, and also calculate the cost if it is 2.5 per unit. So what you need to know, students, is power is 1200 watt, okay, and time, it is 2 hours per day. So in a week, that will be 14 hours. So energy will be 1200 divided by 1000. So that will give me kilowatt into 14. So that answer will be how much? It will be 16.8 kilowatt
So will
hour.
you be sharing all these questions?
Yeah. So I'll
Okay,
share
sir.
it as a PDF, and I'll share the video also. Okay, I'm recording this. Fine. Only thing, I'll edit and share it the video so it is shorter. Another thing over here is the cost. So cost is the number of units, okay, multiplied by the rate. So here you have 16.8 kilowatt hour multiplied by 2.5. So that gives you So the cost will be rupees 42. Okay. Any questions? So you should be expected to solve these type of questions. For a tube light, one day, what will be the consumption? 2 into 60 upon 1000. Okay. And multiplied by how many hours it is used? 8 hours. So therefore, this will be 6 to the 12, 96 upon 100 kilowatt hours. Then for the fan, for one day, it is 110 upon 1000 into 12. Okay, so this will be equal to 132 upon 100 kilowatt hour. And for the refrigerator, for one day, it will be 800 upon 1000 into 10. So we can call it as 80 upon 100 kilowatt hour. This will be equal to 96 plus 132 plus 800, 1028. 1028. And what will be this? 5.20. So 1028 divided by 1000 into 28 into 5.2. So you get 149.6768. So it will be rupees 149.68. So this will be the cost of the electricity bill. Okay, any questions, anyone?
So why do you divide it by 1000?
To make it kilowatt hour.
Okay.
So when we divide it by 1000, you get kilowatt and you multiply it by hours. Okay. Okay. Electrical energy is equal to power into time. So this power is 1 kilowatt hour, which is 125 upon 1000 kilowatt into, I am taking it as T hours. Everyone understanding this aspect? So 1 will be equal to 125 upon 1000 into T. So therefore T will be equal to 1000 upon 125. 25 5s are 25 4s are, this is 40. So that
So
will,
even 1 kilowatt, don't we have to convert it into 1000?
no, this is 1 kilowatt hour. That is because power in kilowatt and time in hours. So kilowatt into hours. Okay, how long will it take to consume 2500 joules? Again, you have energy is equal to power into time. So if you write power in watt and time in seconds, this will be in joule. Do you follow that? If I write power in kilowatt and time in hours, then this is kilowatt hour. Okay, so we have 2500 joules and this is 50 watt into T. So T will be, this is divided by 50,
50 hours.
50 seconds.
Sorry.
So it will take 50 seconds to consume 2500 joules. Remember, power is 50 watt. Okay, power is 50 watt means, just a minute. Power is 50 watt, it means 50 joule per second. That means in 1 second it consumes 50 joules. So how many seconds it will take to consume 2500 joules?
A question like a bulb is rated suppose 50 watt to 20 volt. What do
Yeah.
you mean by this statement?
Yeah,
So
the answer
what
to that statement is when the bulb is connected to a power voltage of 220 volt, it will consume 50 watt. Okay, or it will consume 50 joules per second. There is this bulb. Okay, these are all textbook type of questions, huh? So you should be able to answer this. This bulb, when rated 220, connected to 220 volt, it is going to consume 50 watt. Now, instead of 220 volt, if it is connected to 200 volt, then how much will it consume? Okay, while I was teaching you this, I have always asked this question, what remains unchanged?
The resistance.
The resistance remains unchanged. Very good. Okay, so resistance of the bulb remains unchanged. So therefore, students, what is the formula for resistance? Power is equal to V square by R. Therefore, R is equal to V square by P. So I have V1 squared upon P1 is equal to V2 squared upon P2. So I'll fill up the data. 220 into 220 upon 50 is equal to 200 into 200 upon P2. So I get P2 as 200 into 200 upon 50 upon 220 into 220. So yes, the answer will be in decimals. So this will be 100 into 50 and 11 into 11. So since I'm making up the question, the answer, it's not going to give you like a proper answer. So I'm getting this as 41.32 watt. Okay, any questions, anyone?
So how is it 100 into 50?
This 2 goes with this 22 and makes it 11, and 2 hundreds are, and this 22 also becomes 11. So again, we will use the same formula. P is equal to V square by R. Therefore, R is V square by P. So R1 upon R2 is V1 squared P1, V2 squared P2. So what will I do over here? V1 squared upon P1, and this is V2 squared. So that is 220, 220, and this is 80, 110, 110. So this will be 2 and 2. So what will this be? 6 upon 1, is that correct? So this is the ratio of the resistance. A water in a kettle connected to 220 volt takes 10 minutes to reach its boiling point. So how long will it take if the supply is 110 volt? How do we solve this question? So we have the formula, energy is equal to power into time. Now energy is the energy required for that water to boil. So that is not going to change. What is changing is the power, and that is the reason why the time is changing. Okay, so this particular kettle, we know the formula, power is equal to VI, power is equal to V square by R into T. So V square by R is also the formula for power. And which other formula is there? I square upon R, right? Can anyone tell me which one should I use? 1, 2, or 3?
2.
We should use the second formula. So you have V square upon R into T is the electrical energy. Okay, now since the energy is same and the resistance is same, okay, remember, like in the previous question also we have done, the resistance will also be same. So therefore we have V1 square upon R into T is equal to V2 squared upon R, and this is T1, and that will be T2. So this is getting cancelled. So we have 220 into 220 upon into 10 is equal to 110 into 110 into T2. So your T2 is 220 into 220 into 10 upon 110 and 110. So this will be, T2 will be 4 into 10. It will take 40 minutes. So with a lower voltage, it will take more time for the water to get heated. Okay. Students, anyone has any other question from this part, let me know, then I can solve that. You know that this is medium 1, this is medium 2. A ray of light which is entering from one medium to another medium, it bends. So this is angle of incidence, this is angle of refraction. So refractive index of second medium with respect to first medium is sine of angle of incidence in medium 1 upon sine of angle of refraction in medium 2. Okay, so this is what we know. Now, if the light is traveling with velocity v1 in medium 1 and velocity v2 in medium 2, this is equal to velocity 1 upon velocity 2. If the light that is traveling in medium 1 has a wavelength lambda 1 and in medium 2 it has wavelength lambda 2, then refractive index is lambda 1 upon lambda 2. Okay, so these are three formulas, and there is one more. So if a ray of light which is coming from medium 1 to medium 2, and if you allow it to fall on a mirror perpendicular, so you know that that ray will go back. So if this is the angle of incidence and this is the angle of refraction, now this is the angle of incidence for the light going back, and this is the angle of refraction for the light going back. So we say refractive index of second medium with respect to first medium is reciprocal of refractive index of first with respect to the second. This is principle of reversibility of light. So in the first exercise, you have questions which can be asked based on this. Another part in the first exercise is if you have absolute refractive index, that means refractive index of second with respect to first, in that first medium is air or it is vacuum. So therefore, this is C upon V. What is C? C is speed of light in air or vacuum. That is 3 into 10 to the power 8 meter per second. Fine. Now, what type of questions can you get? So, number one. So just now I told you that refractive index with respect to air, that means it is C upon V. So you have 3 by 2 is 3 into 10 to the power 8 upon V. So V will be 3 into 10 to the power 8 upon 3.2. Okay, so you can say borrow a 10 and this is 3.2. You can make it 300 and this is 32. So this will help to arrive at an answer, and that answer, never leave it as a fraction. You always have to do it. So this is 93.75, okay, into 10 to the power 7 meter per second. We want refractive index of water with respect to glass. Now, which one is correct? A or B?
B.
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 When you have, I just showed you over here, refractive index of second medium with respect to first medium is velocity of medium 1 upon velocity of medium 2. So therefore, this is correct. Glass and water. Okay. So therefore, glass will be, okay, just a minute. I have made one error in this. Like it should be slower in glass and faster in water. So therefore, this will give you 1.8 into 10 to the power 8 upon 2 into 10 to the power 8. So this get cancelled. And
So
this
you written 10 to the power 2 in the question.
Sir, you wrote 10 to the power 2.
that is my mistake. Okay, this should be easy. Refractive index of glass with respect to brine is 5 by 4. So therefore, refractive index of brine with respect to glass will be 1 upon this. The reason is reversibility of light. So we have the answer as 4 by 5, which is 0.8. So that's the third question. Okay, so this is medium 1, medium 2. The light traveling has 250 nanometer as wavelength. So they are asking what is the wavelength in the second medium. It is provided that the refractive index is 1.9, 1.5. So refractive index of second with respect to first is wavelength in medium 1 upon wavelength in medium 2. So this is equal to 250. So this is also 250 upon 1.5 and 2500 upon 15. So this will be 5 3s are 500 upon 3. So that answer will give you 166.67 nanometer. Okay, so just a quick recap of this. This is the water. Okay, so this water has a real depth of F. So anything that is placed will appear to be raised. So this is y. So that is called as a apparent depth. This is called as shift. So shift is x minus y. So let's do a couple of questions based on this. So therefore 4 upon 3 is equal to x upon x minus 2. So you get 4 times x minus 2 is 3 times x. So 4x minus 8 is 3x. So 4x minus 3 is equal to 8. X is equal to 8. So therefore, the real depth will be 8 centimeters. So I received a couple of answers. One answer is 6 by 7. Another answer is 7 by 6. Okay, so which one will be correct? Refractive index is real depth upon apparent depth. So the real depth is 21 and the apparent depth is 18. It appears to be 18 centimeter deep. So this will be 3 7s are 3 6s are. So 7 by 6 is the correct answer. But you cannot leave your answer as 7 by 6. It has to be written in the form. Okay, 1.66. So it will be 1.17. Decimal form you have to write it. I1 plus I2 is equal to A plus delta. And you have R1 plus R2 is equal to A. So this is like a common thing. But when you have minimum deviation, so in that case, 2I is equal to A plus delta minimum. And you have 2R is equal to A. So when minimum deviation takes place, okay. What else do you know about minimum deviation? A ray of light, when it passes through a prism, you bend like this and then bend it again, bend toward the base of the prism. But when there is minimum deviation, this ray of light inside the prism goes parallel to the base of the prism. Okay, so that is why drawing diagram, you need to be careful. Okay, so this is bending toward the base, and here also it is bending, but it is going parallel to the base. What else do you have? You have seen the graph. So for some angle of deviation, you have two angles of incidence. So that is I1 and I2. And when it is minimum deviation, it has only one angle of incidence. Okay, so some questions we have already done in our earlier classes where there was a graph-based question which was asked. Okay, then what else can we do? We go to diagram-based questions of this chapter. 2I is equal to A plus delta minimum. 2I is equal to 32 plus 15 because this is delta minimum.
Yeah.
So therefore 2I is equal to 47. So I is equal to 23.5 degree. So this angle over here is 23.5 degrees. Yeah, so first of all, we calculate the angle of incidence. Now over here, the angle of incidence is this. Since the whole thing is 90 degree, this thing is 90 minus 42 is equal to 48 degree. So this is 48. Now the ray of light is going to suffer TIR. The reason why it will suffer TIR because the angle of incidence is more than its critical angle. So this will also be 48 degree. Okay. Now what we have over here, we need to find the angle of incidence. So a ray of light will suffer TIR. Now we need to know what will be this angle of incidence over here. So this is 42. This thing is 90. So therefore this is 48. So this will be 42, which is a critical angle. So what happens in a critical angle? The ray of light will go, on the boundary separating the medium. Also important for you is to show R is equal to 90 degree.
So,
Yes.
so the angle of refraction for red will be greater than for the green light. Both will bend towards the normal.
Yeah. So over here, like if red is like this, then you have to take green much closer.
Green will deviate more than.
Yeah. So green will deviate more than red. So angle of refraction for red, and this is angle of refraction for green. So angle of refraction for red is greater than angle of refraction for green color. You that the ray that goes like this is number 3. You have to show the path for ray number 1, 2, and 4.
Ray 1 will go undeviated.
Okay, so ray 1 will go undeviated. What will happen to ray 2?
It will show some deviation.
It will suffer refraction. And what happened to ray number 4?
Total internal.
It will suffer TIR. Okay, if someone asks you why, so you have to say that the angle of incidence over here is greater than the critical angle, because this will be your critical angle. Okay. Then there was one more question. The prisms were kept this way. Is this the correct way combination or correct orientation?
No, sir.
Is this the correct orientation?
Yes,
This is for the periscope. Okay, so that is the correct orientation, right? So remember, students, when we have this diagram of a prism, so you have a ray of light which is striking like this. It goes and it reflects back. Okay, so in the same way, what I want you to understand that it is striking the surface containing 90 degree and not the hypotenuse. So over here, if you have a ray of light entering, it is going to hit the hypotenuse. So that's wrong. So here you can see that a ray of light is incident the congruent sides, and then here also it is incidenting the congruent sides, and then in this particular case it will go there. So therefore these are also not like the correct orientation. So we will have to orient it like this. So this will go this way and come back. So that's another question I have seen in one of the paper. Right. Anyone else has any question? In light-based numericals or diagrams, we can take that. Else, then we can do a little revision of calorimetry also. Okay, can we go to calorimetry then?
Yes, sir.
Fine. So let me ask you one question, which you try to solve. Okay, a basic question I'll ask. So calculate the heat required to take water, to take ice at -3 degrees Celsius to water at say 40 degrees Celsius. Calculate the heat required to do that. How many of you know this? Can you just show your thumbs up or something? Okay. Three people know it. Fine. So when you have ice which is at -3 degrees Celsius, you will take it at ice to 0 degrees Celsius. So to do that, you have mc delta T. There is no change in state. The change in temperature is happening. Then you take it at water at 0 degrees Celsius. So that is melting. That is m into L. Then you take it at water, which is 40 degrees Celsius. So that is mc delta T. So there are 3 steps in this. So therefore heat required will be mc delta T, ml, and mc delta T. So here I've not given the mass. So we'll take the mass as say 20 grams. So this is 20 into 2.1 into 3, 20 into 336. and 20 into 4.2 into 40. So this will be 6.3, 336, and 168. Please tell me if you have not understood any part. I will explain again. Okay, this is basic. Has everyone understood? So this is 10206 joules. So this is hot water, this is cold water. We are writing mass, initial temperature, final temperature, change in temperature, so that can be written as delta T. So hot water is 500 gram, which is at 80 degree. Cold water is 300 gram, which is at 20 degree. So again, like I told you, you cannot have negative values. So this I write 80 minus T, and here I write T minus 20, because T will be between 80 and 20. Then we write down the statement: if no heat is lost to the surrounding temperature, then the heat lost by hot body is equal to heat gained by cold body. So we have M1 C1 delta T1 is equal to M2 C2 delta T2. So that is 500 into 4.2 into 80 minus T, and this is 300 into 4.2 into T minus 20. So this get cancelled. I can cancel these two zeros. So 5 8s are 40, and this is 3T minus 60. Okay, so we get 460 is equal to 8T. So 460 upon 8, 57.5 degrees Celsius. So this is the final temperature that you will get. Anyone has any difficulty understanding this? So we have water, we have ice, mass is 150 grams, this is 10. Initial temperature is 50, this is 0. Final temperature we don't know. Specific heat capacity 4.2. Latent heat is 336. So again, for those students, there is ice which is at 0 degrees Celsius, that will become water at 0 degrees Celsius, and then it will become water at T degrees Celsius, which is the final temperature. So this takes ml and this takes mc delta T. And to do all of this, the heat is supplied by water, which was at 50 degrees Celsius, okay, which was at 50 degrees Celsius, to turn into water at T degrees Celsius, okay. So again, writing the statement, and then M1 C1 delta T1, and you have M2 C2 delta T2. So we have 150 into 4.2 into 50 minus T, and this is 10 into 336 plus 10 into 4.2 into T. Okay.
You did not add,
Yes.
you did not add ml.
Yeah. This is ml. And here this is 150 into 4.2 into 50 minus T, and I can just cancel the 0. So what do I get in this expression? So I will have 15 into 4.2, that is 63. 63 into 50 will give me 3150 minus 63T, 336 plus 4.2T. So 3150 minus 336 is 2814, and 63 plus 4.2 is 67.2T as 41.875. So 41.88 degrees Celsius. This will be the final temperature. Okay, any difficulty, anyone? We have copper calorimeter and we have ice. So water is 250 grams. So this is the mass. Copper is 50 grams. And ice we have to calculate. Initial temperature, the water which is contained in the copper, so the temperature will be same for both of them. Okay, and then you have ice will be at 0 degree. The final temperature is given to be 5. So delta T is 25, this is 25, and this is 5. Okay. Specific heat capacity is 4.2, this is 0.4, and latent heat is given to be 336. Okay. Now, students, again, this is the knowledge that you need to have, because solving later on the equation is easy. So what you should know, that this is the hot body and this is the cold body. The hot body is losing heat and the cold body is gaining heat. So in the same way over here, the ice will melt and the ice temperature will rise to 5 degrees Celsius in this case. And over here, water and calorimeter together will lose heat. Fine. So what do we get? M1C1 delta T1 plus M2C2 delta T2 is equal to M3 L3 plus M3C3 delta T3. So we have water, which is 250 into 4.2 into 25, copper, which is 50 into 0.4 into 25, and this is M into 336, M into 4.2 into 5. So this is going to give us an answer. This is 250 into 0.4 into 25. So this is going to give us 26750, and 4.2 into 5, 21 plus 336. So this is 357 M. So M will be 26750 upon 357